Hello, my name is Mark Banchy. I am flight software lead for the GPX2 3U CubeSat. And I'm here with David Keck, who was the ground software lead for the CubeSat. So I'm here to just talk about what we did, a little bit about the project. So here's just an agenda. We go over the mission objectives, where we are today, a little bit about the flight and ground software architecture, ground software architecture, and then I'm going to go over some lessons learned, and I'm just going to kind of take it through the project lifecycle because I thought that made the most sense to talk about. Yeah. So what is GPX2? It's a 3U tech demo. Its goal was to it was kind of a shotgun approach at TRL boosting of a couple different technologies. We built our own flight computer on a pretty limited microcontroller. We're flying a couple cameras that are used on a couple other projects. They're sought after by a lot of other CubeSat projects. And our chassis was actually made out of a kind of a unique material. I know this is software, but this was actually a very interesting thing that we did. A lot of other projects, or there are a couple other projects that have built stuff out of this material. It's a additive manufactured material, but we built an entire chassis out of it, which I believe is we were the first people to do that. And we did a lot of testing on the ground to figure out how to do that and how to do it well. But it's very lightweight, it's very strong, and it's inexpensive. So it's kind of a nice material for people who might want to build a CubeSat out of it. We wanted to increase our knowledge with Iridium short burst data. So we have our primary comm our only comm is the Iridium short burst data. So if you're not familiar with the Iridium network, it's a constellation of satellites, and it's basically a sat phone. You can buy these modems on the ground, or you can buy these modems and they operate on the ground, but it turns out they also operate in space. So Ames has used this on a variety of their tech EdSat CubeSats. So it's kind of a nice platform because you can test command and telemetry in a flight-like way on the ground, which is kind of neat. But it's also inexpensive. It's a couple $100 modem. You're limited in a lot of ways. The data is really expensive, and they're really small packets. So you're talking about 340 bytes up, 270 bytes down. So it's very limited. But we kind of shove everything through this bottleneck, and we were kind of able to do a lot with this really limited system. And I think we're both very proud of what we were able to do with this very limited system. Just to give you some context too, this project is very, it's a white space project. We're kind of just, we work other jobs, we work other, not other jobs, but other projects. This is kind of a white space activity for us. So someone came up to us, had a technology demonstration idea. We had, very limited budget, very limited platform, quick turnaround. What can we do with the limited resources we have? So kind of one of the main things we actually did want to demonstrate was this align experiment with the Novatel OEM 719 GPS receivers. So on the ground, it's kind of an off-the-shelf mode in these receivers that will, in the right configuration, you can measure the distance between these two antenna. So you can measure it really accurately. So the idea is that eventually on-orbit operations or docking or autonomous docking, things like that, you maybe be able to use these to get a relative vector between the two units. So our goal was kind of to just turn these on off the shelf with a couple special configuration parameters, see if they work, what kind of things we can test on a quick turnaround project. The other big thing is this is workforce development. We're all very early career engineers. We were all very young on the project. It was a very small team. So I think we succeeded in that, learning a lot. So where are we today? We launched in July. We were at Virgin Orbit's first night launch, which is exciting, I guess. For us, it was on the East Coast. They launched at night on the West Coast, so we were up at 4 a.m. commissioning the thing. Yeah, we successfully reached our orbit. We were the first payload, I believe, in the group to receive our health and status due to the Iridium network. We've pushed a lot of data through Iridium so far, about 1 megabyte through, which actually is quite impressive for the for the system. And we've taken a lot of images, which I'll show later. And we've tried a lot of these align experiments. So we have no active attitude control on the system. We really were trying to keep the system simple. So we have passive control. We don't think that was enough to achieve a lock in this align mode, but we're still kind of investigating that. But otherwise, we've been operating very nominally. The health of the spacecraft is still very good. So like any good software talk, I'll start out talking about the hardware. So we are flying a STM32F4 chip. We're running 16 megahertz clock in there. I believe the chip can go up to 168, but we decided to run it as slow as we could. We have about 200 kilobytes of RAM, 1 megabyte of internal flash, a DMA controller, a couple other things, but we also added 32 megabytes of external flash on our flight computer board. And we're running free RTOS, and the ground software was written in Python and utilized the Cosmos ground station. I'm going to hand it over to David for the ground software stuff, but I'll be back.
Thanks, Mark. So I will start by covering the ground software architecture really quick. So if we look at our diagram, we can see that there are 2 data paths for GPX2. One of them is a dotted line and the other is a hard line. So the hard line is a hardware connection. That's a UART USB cable. And the other one is our Iridium modem. So both of them have the exact same data layout. We're using the Space Packet Protocol, CCSDS. But there are minor differences in how that data makes it to our ground system. So I'll start with the hardline, the GSE. So what we do is we connect to our laptop, and we have Cosmos run on the laptop, and that's the main connection. So our GSE tool connects also to Cosmos. Cosmos has a local server running on that laptop. And as far as Cosmos is aware, our ground software is totally transparent, has no idea we're listening. So our Python tool, which we call the GPX2 GSE, listens to any data that flows through there in either direction, command or telemetry. And we capture that data just as binary, and then we independently reassemble it. And there's a reason for that, which I'll get to in a second. Once we receive the data, we insert it into a database, which is hosted on a LARC server. And we keep every level of that data. So what I mean by that is we keep binary data. As soon as we've parsed the CCSDS, we keep the CCSDS header with the binary portion up until the fully processed data. So that could mean, maybe we have an ADC packet, which are just ADC counts. And then we also have to parse that up into temperature. And the reason we do that is just in case there's any issues with the fully parsed data, we can always roll back the clock and look at the binary data and see, hey, was there something wrong in the binary? And then if we move over to the modem side, so this is a little bit different because the modem provides kind of metadata about each of the sessions that occur. So we can have a session that has no data, just a failed session, an attempted session. Or we can have a session that completed the data downlink, but it wasn't sure of its location. So we want all that information in case it's useful for operations. And it turns out it is useful because Iridium can say that a session was incomplete. So it'll say, hey, I wasn't able to complete that session, but it actually did. It received the command. So our flight software saw the command, but Iridium didn't think the session completed. And that's been very useful because we'll see commands be processed more than once. Despite the fact that we're handling it correctly in the flight software, the return code we get from Iridium is saying, hey, yeah, I'm going to retry that session. So we get the command again. Hasn't been an issue for us. We kind of have resilience in the flight software, so haven't had any major problems from that occurring. So once we get the emails, we parse those, using the same tool. There's 2 modes on that tool, so we can go Cosmos mode or email mode, and all that gets uploaded into the database on our server. All right, so now we're into the lessons learned. So the first one I want to start with is open source is great. You can build on the work that other people have already done and enable functionality that you might not have had the time or budget for otherwise. And that's certainly the case with us. We're a very small team, and a lot of these tools unlock things that just wouldn't have been possible otherwise. So I'll cover a few of these in a little more detail later, but I do want to shout out a couple here. So Lua is running on the DGPS receivers. So that's actually how we run our experiment. We tell the DGPS receiver, hey, please run that onboard Lua script and send the data our way, and we'll shove it into our file system. And then DeerPy GUI was used for all of the graphical interface on all the ground tooling. And of course, static analysis, we're using Cobra. I believe Gerard gave a talk in last flight software workshop. Excellent static analysis tool. All right, so now we'll get into part of the design and development here, the flight software. So as we started implementing more and more of the subsystems, we started realizing, hey, this platform really is constrained. There's no way we can handle all these interrupts from the camera, from the IMU, ADC, DGPS. And so we started moving each one of those to use the DMA controller. And that unlocked a lot more bandwidth for us, and we were able to meet our targets once we were able to do that. So make sure you leverage that if it's available on your platform. And then next up, we went with a trade study to figure out a file system. Now, FreeRTOS does not include a file system by default. So we ended up going with LittleFS. We did look at some of the FAT file systems, but LittleFS actually has some functionality that is kind of more common on servers or desktop OSs. We get wear leveling, power loss resilience, CRC for every block, and we are able to say, here's the amount of memory you can use LFS. You cannot allocate any more. And that's actually worked great for us. We haven't had any major issues with our file system, no corruptions on orbit. But the lesson here was really how much having a file system unlocked more simplicity in our flight software. Because before, we kind of had to depend on any data that was waiting until we could downlink it. But now we can say, run the DGPS experiment, store all the data, and then go back to idle. And if I want the data, I'll ask for it. And we can query the file system to say, hey, what are the sizes of the files for an image or for the DGPS experiment? That's been really useful because we can run calculations to see, did we capture all the logs we expected for this experiment? Did it end early? And since the images are JPEG compressed, we can say, oh, this image is really small. It's probably looking out into space. We don't want to download that one. All right, so I talked about the database. Database is great, but not everybody on the project is going to be thrilled about having to access a raw database to see the data. So on top of that database, we're using a tool called Grafana. And this tool kind of allows you to build your own views for time series data pretty easily. And it ended up being a big hit with folks on our project. So what this allows is a centralized location, for TVAC, for flight, for testing, where you can go and say, I want to see what's currently happening in that TVAC test. And maybe thermal wants to roll back the clock and say, hey, where were we temperature-wise 4 hours ago? They can make whatever view they want. And this was really nice for flight. So like Mark said, we got our first packet about 45 minutes after we were deployed. And everybody on the team was glued to that Grafana page. And as soon as we processed it, everybody could see the data and be on the same page. And with that, I'll pass it back to Mark.
Yeah, so kind of the theme here is we were very resource constrained. And the short burst data bandwidth was significantly more limiting than we thought it would be. We really are only getting about 3.5 to 5 kilobytes a day, which is really not impressive. But what we were able to do, and I'm glad we did this, it was kind of a last minute thought. We had a little bit of extra time in our schedule, and I had a harebrained idea, and David was willing to implement it with me. We basically are able to split telemetry and downlink certain fields and certain periods of that field. So we know, the telemetry is a fixed length. We have rolling buffers for each log type. And we know the layout of those fields, obviously. So we're able to send a special command that we can define up to 5 different slices into that data. So we can span sections of data, or we could do one field, skip a bunch of data, do another field. And we can request a period of, give me every 4th sample, give me every 10th sample. So by doing that, we're able to get long-term trend data on the health and status of the spacecraft that we wouldn't really have been able to do otherwise. So this has kind of started out as an idea that we didn't think would really we'd really use, but it turns out it's our primary way of really getting information about the satellite. A lot of these are going to seem very obvious, but have a flat set for the software team. It's kind of a big deal. If you don't have something to test on, you don't have something to develop the software early, it's going to be a lot more difficult later on in the project. And that allowed us to catch a lot of stuff early, and it made the second half of the project, the integration and test portion, a lot smoother than I think it could have been. Automate your system level tests. So we used Cosmos. If you're familiar with Cosmos, there's a test runner framework in there. So we basically wrote system level tests that were kind of like unit tests for the satellite. We check a dozen things. We send every command in the system. We run day in the life. We do long duration tests. We do outdoor testing. We had an indoor suite. And it was really nice to be able to click a button and watch it all execute. And people kind of looked at us and were like, is that it? Is it really working? And we're like, look at this 50-page log of what it did. So be lazy, I guess, is my my advice. And this one's a little bit stands out a little bit because it involves staying connected with vendors. So we had an issue kind of late breaking in TVAC. Our duty cycle, or our heaters during one of the duty cycles, cut off early at 3 a.m. I received a call. We were like, the heaters are cutting off. What's going on? So we took a bit of digging, but we discovered it was actually an issue in the power subsystem. So we use a GOM-based power subsystem. There's a configuration in there, but it was silently resetting, and it wasn't really telling us about it. Luckily, our flight software didn't reset because of the way we had architected the power, but the system that controls our power was resetting, and it was doing it silently. So we eventually contacted them. They got back to us, and not only did they admit that there was an issue in there, they knew about it. They had a patch for it, and they had never contacted us about it. So it's a little frustrating. I was a little frustrated about it, but at the end of the day, we should have probably reached out to them as well to see, hey, we're flying this hardware we got a couple of years ago. Any updates that you have? Because at this point in the project, we were literally integrated into the TVAC chamber, so we didn't really have a chance to update this piece of software. We would have missed our launch and all that kind of stuff. So we had to patch it. We patched it in our own flight software, and it's basically just a workaround. We were able to turn off the timers that were basically reset on this in their system. So we have to send now a command after we launch to turn these off. But that has proved very successful. The system is silently resetting as we speak, about 4 times a day. We see it, but it does not affect the flight. So we successfully mitigated this issue, but it could have been a lot worse depending on how we powered our flight computer. Plan for ops. Again, these are all obvious, but flight software engineers tend to know the most about the system and how the data works, and we can become operators on small teams if you're not careful. I enjoy operating it. It is white space effort, but plan for that stuff and get funding to do that kind of stuff. And automate these things, which we're kind of slowly doing over time to free up more and more of our time as we're, working on other projects and things. But this is actually the first image we took from the satellite. It's just of the, I think it's the Pacific Ocean. We were off the coast of Chile, I think. Yeah, there's more pictures. But in conclusion, 3U tech demo on a shoestring budget with a green team. We learned a lot of things. We're really proud of what we did. Leverage the tools that are available to you. I think what's often forgotten about this kind of lesson, and these are all very obvious, but the first step is to learn what tools are available. We get really comfortable working with the same tools. I think it's important to take some time and play with new tools and see if they'll be useful to you. I certainly think we wouldn't have done half the things we did if we didn't spend the time doing those kinds of trades. This one's obvious. Good software designs pay dividends. I think we had a really solid design that allowed us to add and remove things very effectively. It let us be very nimble. Automate things, work smart, not hard. Embrace being able to fix it in software. I know a lot of us get annoyed when someone else's subsystem isn't working right and software has to fix it. But that's kind of a superpower for us, I think. I think we need to really embrace that and not be afraid to do those kinds of things. It's more work at the end of the day, and we're stressed in that situation, but it's something unique to our discipline that I think people need to embrace a bit more. Stay connected with your vendors. Yeah, so we're just going to continue monitoring its health and status. We're taking more photos. We're running more line experiments and tweaking settings and things. But really, we are applying all these lessons for future CubeSat projects. David and I are both working on a couple other CubeSat projects. So these lessons are really to seed those efforts at the end of the day. Here's some photos. We actually have more photos that we took since we made these slides. They're actually even, I think, even cooler. But the coolest one is that's Hurricane Ian on the bottom middle. We got lucky and snapped one of that right before it made landfall. The bottom right actually is one shortly after landfall. That's the Gulf of Mexico. You can kind of see the coastline of Florida. But yeah, happy to entertain any questions for myself or David. Thank you.